Hi, my name is Shivank Misra, and this is my video lab report for Intro Physics 2211 at Georgia Tech. This lab examines the mass of a black hole calculated by analyzing the motion of a star orbiting the black hole. I'll first introduce some key ideas, relevant formulae, and explanatory diagrams. I'll then discuss my computational model, its use of Newton's second law, the method by which I determine the mass of the black hole, and the data produced by my model. And finally, I'll answer some essential questions about the lab. So firstly, some of the key ideas relevant to this lab are Newton's second law of motion and the momentum principle, which are used to calculate the net force acting on the object in the computational model, the product rule for differentiation, and Newton's universal law of gravitation, all of which I'll be explaining further. So here we have one of the most important formulas for this lab. dp dt refers to the rate of change of momentum, denoted here by the vector p. Now any vector can be written as a product of its magnitude and its unit vector. We use this fact when taking the derivative of p and apply the product rule for differentiation to obtain this formula. Now by the momentum principle, the net force acting on an object is equal to its rate of change of momentum, so we can therefore write F net equals dp dt as I've done here. Looking at the result we obtained on the left, it becomes apparent that the two terms in the equation are simply the parallel and perpendicular components of dp dt. And since dp dt is equal to F net, we can similarly write the parallel and perpendicular components of F net, which I've done to the right. This diagram on the right also helps us visualize this, where the blue arrow is the parallel component of F net and the purple arrow is the perpendicular component of F net. Moving on to more formulas, we know that since F net equals dp dt, the magnitude of F net must equal the magnitude of dp dt. An assumption we make in this lab is that the only force acting on the star is the force due to the gravity exerted by the black hole. Hence, the net force can be set equal to the force of gravity, and their respective magnitudes are also equal. Therefore, the magnitude of dp dt is equal to the magnitude of the gravitational force, yielding this equation. This can be reshuffled to solve for m2, the mass of the black hole, as is done here. Now moving on to the computational model. You can see here where I've set my initial conditions. Special attention should be paid to the mass of the star, which is a known value, and the time interval, which I've set to 86,400, the number of seconds in a day. Now here I'll explain how I applied Newton's second law to my model. Firstly, I pulled the velocity data from the x-vel and y-vel lists. Then I found the initial and final momentums and used this along with the initial and final velocities to find the change in momentum and velocity respectively. I then found an approximation for dp dt and set this equal to F net as per Newton's second law. And then finally, I used some simple vector calculations in algebra to find the parallel and perpendicular components of F net and dp dt. To calculate the mass of the black hole, I applied this formula as seen here. I then added the mass to a variable called sum mass and increased the value of a counter I created. Then at the end, I found the mass by taking the average of all the masses and divided sum mass by the counter. Here's a video of the program in action. And as can be seen here, the final mass of the black hole is found to be 1.13 times 10 to the 34 kilograms. The data you saw being printed just a moment ago is presented here in graphical form. I've graphed the magnitude of each of the force components against time, as well as the magnitude of the overall net force against time. From these graphs, we can see precisely how each component varies over the course of the star's trajectory. Something else to note here is the slight jitteriness of the magnitude of F net parallel. This is likely a computational artifact which affects not only F net parallel but also F net, as seen on the graph to the right. One improvement to this lab as a whole would be to find a way to avoid this jitteriness, possibly by using a computer with a more powerful processor. So what's the difference between net force and its parallel and perpendicular components and the rate of change of momentum and its parallel and perpendicular components? Well, mathematically, there is none. The formulas to the right prove that they are in fact equivalent. The main difference for this lab is that the rate of change of momentum is something we can calculate through direct observations of the object's position, velocity, and momentum as a function of time, whereas the net force is not something we can calculate without actually knowing the mass of the black hole. And what if the black hole was replaced with a new black hole with no change in the motion of the star? Would we be able to tell the difference? Well, simply put, no. If the star's motion is identical, then this implies that the mass of the black hole is the same. Throughout this entire lab, the only property of the black hole that we calculate is its mass. So simply changing its mass would change absolutely nothing for us, and in fact, we won't even be able to tell the difference, as all our calculations would lead to the same mass as before. Thank you for your time and have a nice day.